So throughout the duration of this class, I'm going to be asking you guys to solve for things like voltage, current, power, energy, all that kind of good stuff. So we're just going to spend today talking about how those concepts are interrelated to each other, how we are going to approach them from a circuit analysis perspective, and all of that kind of good stuff. So the first of the basic electrical quantities that we're going to talk about is voltage, because that's probably the thing that we're most familiar with, right? So anytime that we've ever had to change the batteries in something, we have been dealing with voltages. So mathematically, voltage is defined as follows, and I promise you I'm not actually going to make you do line integrals at any point in this class. Okay. So a voltage BA will be equal to the integral from A to B of the electric field vector E dotted in to a differential line element DL. And Ashton is having flashbacks from the field class that I taught her 10 years ago at this point. I fully understand that the overwhelming majority of you guys have not yet had Physics 202, so we're not actually going to use this definition to do anything. We're just going to talk about what it means and then use that context to describe what voltages are in our case, right? So it's perfectly reasonable if you don't understand what electric field vectors are and all that kind of good stuff. That being said, I am going to supplement this relationship with another electric field vector related relationship so that we can have some understanding of what voltage actually means, okay? So there is a quantity called the electrostatic force, F sub E, that is equal to charge Q multiplied by the electric field vector E. Okay. So what I'm going to do is I'm going to substitute this electrostatic force relationship into my voltage relationship. And what that's going to give me is 1 over charge times the integral from A to B of our electrostatic force dotted into our differential line element DL. Now, for you mechanical engineering types, or really anybody that's paid attention in physics class, what is the integral of F dot DL? Force applied over a distance. Work, right? Yeah. So this guy right here is just work. So from this, we can see that one of our definitions for voltage will be the work or energy per unit charge, because we have that factor of 1 over Q out in front, needed to move 1 coulomb of charge. I'm going to write out coulomb and then give you the unit C here. Between 2 points in a circuit. So this mathematical definition tells us that it requires energy or work to move charge around our circuit, and that this amount of work per unit charge is what we call voltage. So voltage is what's providing the push to move electrons around in a circuit. Okay? So in physics talk, we call this an electromotive force because it's moving electrons. Okay? There's a little bit more nuance to that, and if you want to learn about it, go talk to Dr. Stroud or a physics teacher, because I am not one of those. He might actually be slightly upset that I like to prefer to call all electromotive forces voltages when that's technically not true, but as an electrical engineer, I don't care. That's his problem, not mine. Okay. So this is one of our definitions, and it's really telling us what voltage does, but it's not really telling us how we're going to look at voltage in the context of circuit analysis, okay? So what do we know about work or energy? Is it conserved? I would argue that the law of conservation of energy tells us that it is a conservative quantity, right? Energy cannot be created or destroyed. Therefore, work has to be a conservative property as well, because work is just applied energy. So one of the great things about line integrals when we're dealing with a conservative quantity is that they're path independent. So all that means is that I really only have to care about what's happening at the end points of my integral. It doesn't matter how I get from point A to point B or what path I take, I'm going to get the same mathematical result. And so from that, we could actually say that this is just the voltage at point B minus the voltage at point A. So an alternative definition, and one that we're actually going to use a whole heck of a lot in this class, is that voltage is the difference in electric potential energy between 2 points in a circuit. Now, whether or not you guys realize this, this is the definition of voltage that you've been using anytime you've tried to measure it. What do you measure a voltage with? A voltmeter. How do you measure a voltage with a voltmeter? You have two leads. You put one at one point in the circuit, the other lead at a different point in the circuit, and then it tells you the potential difference between those 2 points. That is literally what a voltmeter is doing. And it is this exact definition, and it works because of the math behind this, right? So students tend to get hung up on this concept of electric potential energy and the difference between 2 points because they think that voltages require a closed path or anything like that, but that's not remotely true. If I have 2 points, I can measure the potential difference between them, regardless of whether or not there's any current flowing between those 2 points, either directly or indirectly or anything like that. That's exactly what our multimeter is doing. We're just taking 2 arbitrary points on our circuit and letting this device tell us what voltage drop occurs between those 2 points. So I'm trying to break you guys' habit of thinking that you need a current to be flowing in order to measure a voltage, because that is not remotely true, and we're going to see that over and over and over again in this class. So energy is a conservative quantity, right? So we know that the law of conservation of energy says that energy cannot be created or destroyed. Work is nothing more than the transfer of energy. So the amount of energy transferred has to be summed to zero in a closed system. All right, so we've talked conceptually about what voltage is. Now let's talk a little bit about how we are going to represent it in circuits, okay? So I'm going to start with a generic circuit element. Let's call this circuit element A, okay? And I am going to say that I have a voltage VA here that is equal to 5 volts. Now, this is an incomplete representation of voltage, okay? So to this point, I have told you guys what the magnitude of the voltage is, but in this class, we are going to be dealing with polarities as well. Okay? So I'm going to arbitrarily choose to put the positive polarity terminal on top and the negative polarity terminal on bottom. All that means is that the positive polarity terminal is at 5 volts higher electric potential than the negative polarity terminal. It doesn't have anything to do with literally anything else, okay? So this is just the positive polarity is higher than the negative polarity terminal by the magnitude. So if we have a AA battery in our hand, the positive polarity terminal, which is indicated by a plus sign on the battery, is 1.5 volts higher in electric potential than the negative polarity terminal that is usually indicated by a minus sign. Now, what would happen if I flipped the polarity of the voltage drop across this generic element A? Exactly right. If I change the polarity, I'm going to multiply the magnitude by a negative sign, okay? So with positive polarity on top, we have positive 5 volts, then positive polarity on bottom means that we must have negative 5 volts. So anytime that we see a negative voltage, we can make it appear positive simply by changing the polarity. I don't know about you guys, but I am hot garbage when it comes to dealing with too many negative numbers and making sign mistakes and stuff like that. So the overwhelming majority of the time, anytime I see a negative quantity, I'm going to try to do something to get rid of those extra negative signs so that I don't make simple mistakes. So this is the American style of representing a voltage in a circuit. Right? Includes a magnitude and defined polarities using a plus and a minus sign. Now, because some of you guys are going to watch YouTube videos and all this kind of stuff to help you figure this stuff out, I'm going to introduce the European style, which I personally find confusing, but it is used by a whole hell of a lot of people, so it's probably good that you guys have some idea about it. Yes, sir. No, I don't look at your work. It's a multiple choice test, so whatever gets you there, gets you there. Are you an electrical engineer? Okay, good. Meaning I won't have to deal with your hippie witchcraft in later classes. Okay. So the European style let's call this guy B. We would still have our magnitude. Let's make this 10 volts just because it's something different. And then I'm going to do the arrow in a different color because it's going to be going through this. We would represent the polarity using an arrow, which is very, very strange to me because as an American, I'm used to using arrows to represent currents, which we'll talk about here in a moment. It's usually a curved arrow, not a straight arrow. That being said, straight arrows do exist in some documentation and all that kind of stuff. The head of the arrow is representative of the positive polarity terminal, and the tail of the arrow is the negative polarity terminal in the American style. Because to me, like I said, currents are represented by arrows. You will never see me do this again because it confuses the hell out of me. That being said, I wanted to make you aware of it just in case you happen to watch YouTube videos or whatever that happen to use this convention. And then obviously, if we wanted to represent negative 10 volts, we would just change the direction of our arrow. So not ever going to use this again. Just wanted to make you aware of it. And then the last way that we could represent a voltage in this class, which we will do this in a modified form, is what's called the double subscript notation. So I'm going to label this top terminal B and this bottom terminal A. And I'm going to say that VBA is equal to 8 volts. So how the double subscript notation works is that the first letter in the subscript is the positive polarity terminal, and the second letter in the subscript is the negative polarity terminal. So this is saying the potential at terminal B is 8 volts higher than the potential at terminal A. If we wanted to say, if we had VAB, changing the subscripts is the exact same thing as changing the polarity. So this would look like negative 8 volts in magnitude. So in this class, we are going to use the American style 99% of the time. And then we're going to use the double subscript notation really when we're using or applying nodal analysis with the understanding that our reference point is ground or 0. So we're just not going to give it a second subscript. But we'll get to that in 2 weeks' time, roughly. All right. Yes. Correct. The first letter in the subscript is the positive polarity terminal, and the second letter in the subscript is the negative polarity terminal. Absolutely correct. Any other questions about anything that we've talked about to this point? All right. So the next thing that we're going to talk about then is the different type of elements that are going to provide voltages or supply voltages in the circuits that we're going to be dealing with. Okay. There are going to be 5 of them that we will see in this class. Okay. And the last 2, I will tell you from the jump, can be confusing. So I'm going to harp on them quite a bit. So the first one that we're going to look at is a battery. So I'm intentionally leaving a gap here because this is something that you've probably seen. You may have also seen this representation for a battery, and there is a technical difference between the two. This form is for a multi-cell battery. Whereas if you only have the single long horizontal line and the single short horizontal line, that is for a single cell battery. Doesn't really matter whatsoever, but technically there is a difference between those 2 different symbols. The long horizontal line is the positive polarity terminal, and the short horizontal line is the negative polarity terminal. We might represent the magnitude of this with just some number. I'm going to call it V bat, which could be 1.5 volts or 9 volts or other voltages that batteries are capable of supplying, 12, all that kind of good stuff. So this is how we represent voltage provided by a battery. It is what most of the voltage sources that you guys saw in your Engineering 120 series look like, and I hate it. And the reason why I hate it is because it looks too similar to the schematic symbol for a capacitor, which is 2 parallel lines that are of equal length. So if you're writing quickly or you're lazy, you can very easily get the schematic symbol for a battery and a capacitor mixed up. So I don't use this symbol pretty much at all in this class. Instead, I use this guy. So this is the symbol for a generic DC voltage source. I'm going to call this voltage VDC. Okay. So the positive polarity terminal for this guy is the one with the plus sign, and the negative polarity terminal is the one with the minus sign. And there is no conceivable way you would ever confuse this with a capacitor. So this is why I like this particular representation. It can be used to represent any DC voltage source, including batteries. So everything that's a DC source is going to look like that in this class. Later on, we're going to be looking at AC sources. So it's going to look like the same thing as a generic DC voltage source, except that I'm going to put a squiggle in the middle. And that squiggle tells us that we have a time varying voltage. Okay. I'm going to represent the magnitude as VAC, all lowercase, as a function of time. So when I'm talking about DC quantities in this class, meaning that they are constant values and don't change in time, I'm going to use capital letters. And when I'm talking about time varying quantities, I'm going to try to be consistent and use lowercase letters. Okay, so that's also going to give us some hint as to whether we're looking at a DC system or an AC system. So this guy right here is our generic AC voltage source. And these three sources are what are known as independent sources. So an independent source simply means that they are going to, or that they don't depend on what's connected to them. So my generic DC voltage source will supply that voltage VDC regardless of what it is connected to, right? There are no dependencies or anything like that. My battery will supply 7 volts if I somehow found a 7-volt battery pack or something like that, regardless of whether or not it's connected to anything or not. The next two voltage sources that we're going to see are examples of dependent voltage sources. Okay. And one thing that can be particularly confusing about these is that they effectively have the exact same symbol. So I'm just going to go ahead and draw both of them at the same time. And then we'll talk about the difference here in a moment, okay? So the one on the left, I'm going to say is going to be a voltage controlled voltage source. You may see this abbreviated as VCCS. And then the one on the right will be a current controlled voltage source. Or CCVS. Like I said, these two are dependent sources, meaning that the voltage they provide is dependent on some external quantity. So the positive polarity and negative polarity are obviously given by the plus and minus sign. So now let's talk about the magnitude of these guys, because this is where things get a little bit confusing. So for our voltage controlled voltage source, I'm going to say that the magnitude of the voltage is going to be K times Vx, where Vx is just going to be some voltage elsewhere in the circuit that is controlling this thing. So Vx is a controlling variable, and then K is a scaling factor, okay? And this scaling factor K in a voltage-controlled voltage source has units of volts per volt or unitless, right? So we're taking some input voltage Vx and we're outputting some scaled version of Vx where that scaling factor K tells us how much of Vx we actually get. Dependent sources like this are used to model nonlinear behavior in certain elements like transistors and all of that kind of good stuff that is going to be beyond the scope of this class, but we're introducing these sources so that we know what to do with those elements when we finally see them. Yes, Abram. Yes, thank you. Not VCCS, VCVS. Thank you for that. Voltage controlled voltage source. Thank you. For our current controlled voltage source, we are going to have lowercase g times Ix. So this voltage source depends on the amount of current flowing somewhere in our circuit. And our scaling factor of lowercase g has units of volts per ampere. So that G multiplied by some current is going to give us an output that is a voltage. Again, this is just something, a mathematical model that we use to represent a more difficult circuit element to understand what's going on. So if you are ever faced with a problem containing a dependent voltage source, by the way, dependent sources are always going to look like diamonds in this class. And we'll know that it's a dependent voltage source because there's a plus and minus sign in there telling us we have a voltage source. So if we're ever faced with a dependent voltage source, we can determine what type of dependent voltage source we have by looking at what type of controlling variable we have. If it's a voltage, we have a voltage controlled voltage source. If it's a current, we have a current controlled voltage source. You won't always necessarily be given the units for our scaling factors. So I'm telling you right now, if the units are not given, the scaling factor for a voltage controlled voltage source is always in volts per volts. And the scaling factor for a current controlled voltage source is always in volt per amp. I will try to give you guys the unit for those after some discussions that I had with Dr. Swanbaum and the other professors last quarter, because this is very confusing. But I have not had an opportunity to go back through all of my prior assignments and make that correction. So I'm just telling you emphatically, if I don't give you the units, these are what the units should be. All right, so these are our 5 different ways that we're going to see voltage provided to a circuit. Before we move on to current, does anybody have any questions about any of this? All righty, you guys are quiet. So let's go ahead and jump to the next page. Let's talk about current. Actually, I forgot something. Let's jump back here to voltage really briefly. I forgot to tell you guys the units, right? Probably pretty important since I'm harping on units so much and I've actually talked about the unit voltage. The unit for voltage, we can determine from our mathematical equation, right? So we know that work is measured in joules. And then we're dividing work by charge, which is measured in coulombs. So 1 volt is just 1 joule per coulomb. So that's the unit of voltage based on fundamental SI units. All right, sorry for forgetting to do that 25 minutes ago. All right, now that I knocked that out, now let's talk about current. So mathematically, current I is the derivative of charge Q with respect to time. So our total amount of charge needs to be changing in order for us to observe any current flow. Okay. So before I forget about it, this is going to tell us what our units are as well. The unit of current is the ampere, commonly called an amp. And dimensionally, it is measured in coulombs per seconds. So since we have a derivative-based relationship, this is really just telling us that current is the rate at which electrons are flowing in our circuit, right? Or the rate at which electrons pass a fixed point in our circuit, or however we want to talk about that. So I'm going to go ahead and write that down. And I want to talk a little bit here, very, very briefly, about the concept of conventional current and why a dead old guy got it wrong. So conventional current means that we are considering the motion of positive charge carriers to give us positive current. This is what old Ben Franklin gave us way back in the late 1700s, literally before the concept of electrons was ever thought of. Okay? So we now know that electrons are the principal charge carriers for electrical current, which means that the motion of electron flow is actually opposite the direction of conventional current flow. We're not really going to be dealing with electron flow too particularly much in this class. We're just going to call it a current and move along. But it might crop up every now and then. So just kind of have in the back of your mind that Ben Franklin screwed up because electrons weren't invented or discovered until about 150 years after he died. So he had no fundamental basis to figure things out. Anyway, he was just electrocuting his son with a kite. So just to recap things here, if electrons are moving from left to right, positive current is flowing from right to left. Okay, they're just in opposite directions. If protons or positive charge carriers are moving from left to right, current is moving from left to right. So it's just all based on what the positive charge carrier is doing. All right, okay. So we have a mathematical definition for current. We have a word definition for current, kind of explaining what it is. We know that current and voltage are related, and we'll get into that a bit more, especially when we talk about specific circuit elements and all of that kind of good stuff. Just be aware, like I said earlier, voltage is the quantity that's providing the push that causes current to flow. That being said, current can be flowing if there is no voltage drop across a particular element, like a wire or something like that. Effectively, what I mean by that is if there's a voltage in a system, there will be a current in the system, kind of thing. But it's not necessarily obvious as to how those things are directly related to each other until we're looking at specific components, which is what we're going to start doing in our next class meeting. All right, so the equation that I give you guys here can be rearranged to find charge if we happen to know current, right? So charge in terms of current is given by Q is equal to the integral from, let's call this time t naught, to some later point in time t of our current as a function of t prime dt prime plus q at t naught. Okay. So this is an ugly equation, and there's lots of weird little nuance going on in here that I need to explain to you guys. Okay. So the first thing that I need to explain to you guys is what t naught means. Okay. So t naught is just a point in time at which the charge was a known quantity. Okay. This might be t is equal to 0, could be 3 seconds, could be -5 seconds, just depends on the system that we're looking at and when we knew what the charge was doing. Okay. I like to call this an initial condition on the system. Okay. T is just a later point in time when we're trying to figure out what's happening. Okay. T prime, yes. Yep, just a point in time where it is known. I'll usually make it 0, but not always 0. Just 0 depends on make the math equal. Okay. T is just a later point in time. T prime this is just a dummy variable representing time. Okay. So in some of your prior classes, some of your math instructors may have told you about using prime notations to indicate derivatives. I will never do that in this class. Okay. If I want you to take the first derivative, I'm going to say the derivative with respect to a variable. Second derivative is b squared with respect to the variable squared, etc. I will never, ever, ever use a prime notation to indicate a derivative in this class. I'm always going to use primes to denote dummy variables and things like that. Okay. So the reason why we need to use a dummy variable here is because t, time, is in our limits of integration, and it would be too confusing to have the same variable show up twice if we were trying to actually perform this calculus. Now, in your math classes, when you use dummy variables, you very often use the Greek letter representation, which would be tau. Unfortunately, tau has a very specific meaning in electrical engineering related to time constants, which we're going to talk about later in this class. So we can't use the Greek representation. If you just hate using these prime notations, do X or Z or something like that. It's just a dummy variable. As long as you know that it's representing time, it's good to go. Okay. All right, so let's put this equation into practice because it's kind of annoying to figure out what exactly is going on here. So let's say that I have a current waveform that looks like this. So this is going to be I of t measured in, let's make this annoying and call it milliamps. And let's make this axis t measured in seconds. Let's say that this point is 8. This point is 3. And we want to find Q at t is equal to 5 seconds if Q at t is equal to 0 seconds was, let's just say 1 coulomb. I'm not sure how the math is going to work out on this, and I don't want to give this an artificially huge number or artificially small number. All right, so we're going to use this second equation. We're trying to find charge for a given current waveform. Okay. So we would have something like this. So Q of t is going to be equal to the integral from where is our current known? At what point, or excuse me, at what point in time is our charge a known quantity? 0, because that's what this sentence says. The charge at t is equal to 0 seconds was 1 coulomb. So that's our t naught. Okay. So we're going to integrate from 0 seconds out to 5 seconds. We're going to be integrating our current, and then we're going to add to that Q at 0, which happened to be 1 coulomb, right? Since t isn't in my limits of integration anymore, I'm free to use t inside my integral now. Okay. Now, over this interval from 0 to 5 seconds, I actually have piecewise function, right? Because there's one interval from 0 seconds to 3 seconds where I have a linearly increasing bit, and then there's the interval of time from 3 seconds to 5 seconds where my current is a constant value. So I'm actually going to have to break this integral up into 2 integrals for each of the intervals of interest. So that would look like the integral from 0 to 3 seconds. What's my current function look like over this time span? 8/3, okay, so that's my slope. Milliamps per second, because units matter. Times time. Any y-intercept to speak of since we're using the y equals mx plus b slope-intercept form? Nope, not at all. So we can just leave it like this, dt. And then we're going to have the integral from 3 seconds to 5 seconds. I should put units on these things. So what's my current over the interval from 3 seconds to 5 seconds? What's the graph say? 8, right? It's a constant value at 8 milliamps. And then outside the integration, we're going to add that 1 coulomb of charge on. So that plus Q at T naught bit is not inside the integral. Okay. So we should be able to math this up pretty easily. So the 8/3 milliamp per second, that is a constant value, so it can actually be taken outside. What's the integral of t with respect to t? T squared over 2, right? So t squared over 2 evaluated at 3 seconds and 0 seconds plus, and we're going to have 8 milliamps. What's the integral of 1 dt? T evaluated at 5 seconds and 3 seconds, and then we're going to add to this 1 coulomb. So we're going to have 8/3 milliamps per second times 3 seconds times 3 seconds is 9 seconds squared. divided by 2 minus 0. So I'm just going to leave the minus 0 part off. Plus 8 milliamps times 5 seconds minus 3 seconds plus 1 coulomb. So let's see here. So 8 times 9 is 72. 3 times 2 is 6. I feel like 72 is divisible by 6. Is that 12? 12. All right, so 12. Let's look at our units here. So we're going to have milliamps times second squared divided by seconds. So that's milliamp seconds. Then we have 8 times 5 minus 3. So 8 times 2 is 16 milliamp seconds. Plus 1 coulomb. Well, we know that a milliamp is, so this will be 12 times 10 to the minus 3. An amp is a coulomb per second multiplied by seconds plus 16 times 10 to the minus 3. Coulomb per second times second plus 1 coulomb. All of this stuff cancels out. So 12 plus 16 is 28. So this looks like 1.028 coulombs. Can anybody think of an easier way that we could have done this? Because technically speaking, this sucks. I'm gonna scroll back up here. We have a triangle and a rectangle, and I feel pretty strongly that as sophomores, juniors, et cetera, in college, we probably know what the area of triangles and rectangles are at this point in our life, right? So the overwhelming majority of the time, if I'm going to ask you to do anything like this, I'm literally going to expect you to just, let's call this guy right here 5 seconds. The area of this triangle is 1/2 the base, which is 3 seconds, times the height, which is 8 milliamps. The area of this rectangle bit right here is the base, which is 2 seconds, times the height, which is 8 milliamps. Add those two areas together, add 1 coulomb at the end for our initial condition, and you'll get the exact same result, except that you won't suffer through 10 minutes of calculus. So, like I said, the overwhelming majority of the time, the calculus that I'm going to make you guys do is going to be adding up areas of simple shapes like right triangles, rectangles, squares, and all that kind of good stuff. The only actual integration that I expect you guys to be able to do would be for simple polynomials. So squared, cubed, all that kind of good stuff, nothing real wild or crazy there. Sinusoidal signals, so cosine functions and sine functions, and then exponential functions. That's about it. If you can do derivatives of those things and integrals of those things, you have all of the calculus knowledge you need to excel in this class. Literally shouldn't require anything other than that. All right, so we've gone through how to use this pain in the ass of an equation, both the formal way and an informal way of just adding up simple areas. So now let's talk about how we are going to represent currents in circuits. So we really just have the one way to do this. So if this is element A, and I say that there is a current IA of 2 amps, once again, I have only partially defined what my current is. So voltage in this class has both a magnitude and a polarity. currents in this class will have both magnitude and direction. So I'm going to arbitrarily say that the direction for this 1 amp of current is down. So if I wanted to know how much current is flowing up, what would I need to do to the magnitude? Change the sign. So if I have 2 amps down, that's the exact same thing as negative 2 amps up. This is practically the only way that I'm aware of that currents are represented. So we don't have, I guess technically there are double subscript notation for currents as well, but you will never see that in this class, so I'm not going to bother. And it's just, if you wanted to know what that looks like, current is flowing from the first subscript to the second subscript. All right, so any questions about representing currents? Magnitude and an arrow indicating the direction. If we want to get rid of a negative sign, change the direction of the change. All right, let's talk about current sources. So our first current source that we're going to deal with is our generic DC current source. Where I'm going to represent the magnitude as some capital letter quantity, I sub S. The arrow hopefully obviously indicates the direction of current flow. I'm using capital letters because it's a DC quantity. This is a little bit of a trick question in as much as I don't actually expect any of you guys to know this, except hopefully Ashton. I'm not expecting her to actually answer it, though. We know what voltage sources look like because we can physically hold batteries and all of that kind of good stuff, right? There are actually voltage sources around this room, like these receptacles here. This is an AC voltage source. There are DC power supplies, one at every station around this room that are a generic DC source. What does a current source physically look like? So a coil is usually thought of as an inductor. It's got something to do with current, but I would argue that it's not really a current source. It can act like a current source at very specific instance in time, and we'll talk about that when we get to transient analysis, but that's not really what I'm looking for. And again, not expecting anybody to actually know the answer to this question. Current source isn't something that we can usually just go buy from Walmart or Lowe's or something like that. Like you can buy current sources as a piece of electronic equipment, but it's usually from high-end electronics supply stores for laboratory purposes and all of that kind of good stuff. There are several thousands of dollars usually. From a practical standpoint, the current sources that we might deal with as practicing electrical engineers, yes. Yes. That just means the direction. So so circling back around to this previous thing, I'm saying that there was positive 2 amps of current flowing down. So if I want to know the current flowing in the opposite direction, I had to change the sign on my magnitude. So there is no polarity or anything like that to worry about. There's just magnitude and direction. And if I ever want to change the direction, that's the same thing as changing the sign on the magnitude and vice versa. So this 2 amps corresponds to this down arrow. So this negative 2 amps has to correspond to this up arrow because they're in opposite directions. Yep, nope, not a problem. So okay, so let's So let's say that I have this generic circuit element B right here, okay? Give me a current. Tell me literally a number. 4, okay? So 4 amps. Is that current flowing from left to right? Is it arbitrarily your decision? Pick left to right or right to left? Right to left. Left to right, okay. So 4 amps is flowing from left to right, okay? So if I were interested in the current flowing from right to left, that would be the exact same amount of current, but it's flowing in the opposite direction. So I need to put a negative sign on the magnitude. That's how we get rid of negative signs with currents and all that kind of stuff. If we have a negative sign and we want to get rid of it, we just change the direction of the current. So this IS here is a variable, but let's call it 5 amps. That means there's 5 amps flowing up. So whatever IS happens to be, that amount of current is being driven up because the arrow tells us what the direction of the current is. So if I had a current source, a generic current source with the direction down, it means that whatever current it's supplying is going down. It would be negative if we consider up to be positive. It doesn't matter. Yeah, sorry. Yeah, no. So circling back around to what a current source is from something that we might actually deal with, the transistor, right? So if we DC bias a transistor, how a transistor works is we apply some fixed amount of voltage and it drives some fixed amount of current. So all a current source really is just a simple transistor circuit. And we're just modeling this complicated nonlinear circuit by a simple ideal current source. Okay? So we're never going to be able to just really go to the store and buy one of these, but it is a valid model that we're going to be using throughout our electrical engineering career for all of us electrical engineers in this class and all that kind of good stuff. So I just wanted to put that out there. All right, so if we have a generic DC current source, we must also have a generic AC current source. Exact same symbol, except we have a squiggle in the middle of it, letting us know that the current is time varying. I'm going to represent the magnitude by lowercase letters because it's AC. And these two guys represent our independent current sources. That P looks, or that D looks too much like a P. And then we're also going to have 2 different dependent current sources that we have to deal with. Once again, their symbols are going to be identical. So this guy on the left will be a current controlled current source. Or CCCS. And this guy on the right will be a voltage controlled. Current source, VCCS. Abram, did I get my initials correct this time? Thank you. All right. So these are examples of dependent sources. Once again, our dependent sources always look like diamonds or rhombuses or however the hell you decide to describe that shape. And then our independent sources are always going to be circles. Okay. So for our current controlled current source, the magnitude is going to be something like K times some current IX, where K, our scaling factor, has units this time of amps per amps or unitless. And then for our voltage controlled current source, we're going to have a scaling factor of lowercase r times some voltage Vx, where the units on our scaling factor r is amps per volt. And now that I'm looking at this, I'm realizing this one should have been G and the other one should have been R. Doesn't matter. It's just going to be a number for all you guys anyway, but let me go fix that. The reason why that arguably matters, and I apologize for this, is because volts per amps is usually associated with the concept of resistance. And amps per volts is usually associated with the concept of conductance. And that the symbol for resistance is R and the symbol for conductance is V. So I apologize for having gotten those backwards. So Ashton, in your notes, right, for next quarter, don't embarrass yourself and screw this up. All right, so these are the 4 different current sources that we're going to utilize throughout this course. We've talked about voltage to this point, and I screwed up one of the source things and also forgot to give you guys the units. Then we talked about current, and then I screwed up one of these things, but I did remember to give you the units. So arguably I'm improving as this lecture goes on. We'll see if that, yeah. Any questions about anything that we've covered to this point? Yes, sir. Yeah, let's do it. Conductance. And we're going to talk about that later, so you don't really need to know that yet. Like we're literally going to talk about that in our next class. Yeah. Sure. You're exactly correct. They do look the same. So all of these dependent sources all have a diamond shape. So that's confusing in and of itself. So we have a diamond shape. That means we have 4 different options: voltage controlled current source, voltage controlled voltage source, current controlled current source, current controlled voltage source. Okay. So we have determined that it's a dependent source because it's a diamond. All right. If it has a plus or minus sign, it's a voltage source. If it has an arrow, it's a current source. Okay, so now we've trimmed it down. The next thing we need to know is what our controlling variable is. So if it's controlled by a current, it's a current controlled something. If it's controlled by a voltage, it's a voltage controlled something. Yep. Yeah, by looking at it, by looking at the symbol, you can't see. You have to look at what's controlling to get the whole picture. And that's another reason why these things are so damn confusing. Yeah. So I'm not being facetious here. These guys are going to annoy the hell out of you for the entire duration of this class, which is all the more reason that I'm going to use them to get you used to seeing it. Okay? Because if I don't make you practice it regularly, you're never going to understand what the hell's going on. So I'm being a jerk, arguably on purpose. Kind of get used to it. All right. Any other questions about this stuff? All right. So let's tie some things together by talking about work and energy, or power and energy, excuse me. So power is defined for our intents and purposes as the product of voltage and current. I am explicitly writing this as time varying quantities, but it works just as well for DC quantities. So P is equal to V times I, or for those of you that had Dr. Corbett in your Engineering 120 series, you can remember this by I've got the power, I times V is equal to P. Whatever floats your boat works for me. Okay? So power is always just current times voltage. We're going to develop power relationships specific to resistors, capacitors, inductors, all of that kind of stuff, but we can always go back to this fundamental relationship. Power will always be I times V. Okay. So we're going to define power is the amount of energy, or actually, let's fix that. The rate at which energy is absorbed or supplied by a circuit element. So we can have a second definition, mathematical definition, that power is just going to be the derivative of energy, W, with respect to time. Where power is measured in watts, symbol W, which is defined to be 1 amp times 1 volt, or 1 joule per second. And energy is the integral of power. From some point in time T1 to some point in time T2. So we can say that energy is the total amount of power absorbed or supplied over a fixed interval time. So in both of these definitions, I have used a nomenclature of absorbed energy, absorbed power, supplied power. And this is another one of those things that can be rather confusing in this class. So I'm going to talk to you now about a concept called the passive sign convention. And I am going to try to present it to you in the simplest terms that I can, with the understanding that it really just takes a significant amount of practice to make sense of this thing. Okay? So let's say that I have a generic circuit element, A, that is part of some larger circuit. That's what those ellipses do there. Okay. I'm going to define the voltage drop across element A to have the positive polarity terminal on top. And I'm going to define the current flowing through element A to be flowing into the positive polarity terminal. Okay. So the current IA is flowing into the positive polarity terminal of the voltage VA. Okay. In this case, the power absorbed by element A is just VA times IA. And the power supplied by element A is negative VA times IA. So absorbed power is just the opposite of supplied power. If our current is flowing into the positive polarity terminal, I times V is the absorbed power, and negative I times V is the supplied power. Now, I did not put any restriction whatsoever on the sign of our current IA or our voltage VA. Okay? So if IA were positive 2 amps and VA were negative 3 volts, this thing would be absorbing negative 6 watts of power or supplying negative 6 watts or positive 6 watts. Okay. The opposite condition is this. So here's generic circuit element B. I'm going to define the voltage drop across VB with positive polarity on top. And now I'm going to say that current IB is flowing into the negative polarity tank. For this situation, the power absorbed is negative VB times IB, and the power supplied is positive VB times IB. So the passive sign convention really is just if the current's flowing into the positive polarity terminal, call it absorbed power. If the current's flowing into the negative polarity terminal, call it supplied power. That's all the passive sign convention really boils down. There will be times in your homework assignments, all that kind of good stuff, where you're working on stuff and you're doing everything absolutely correct, but web work is telling you you're wrong. And then when you wind up changing the sign, you get the correct answer. And the reason is because you don't fully understand the passive sign. I'm giving you this as a fair warning. On my exams, and for those of you that have taken this class before, you're all aware that I make all of the exams for this class. So if you're taking this class, I'm a large part of the reason why you didn't pass the first time. So feel free to call me an asshole. But on my exams, I am absolutely enough of a jerk to put both the correct answer and the answer of the opposite sign on there. I'm expecting you to know the difference. This will show up on every single one of your tests multiple times throughout the duration of the quarter. Understanding this is literally the difference between letter grades on every exam that you will take in this class. Okay. So it is critically important that you try to make sense of it as soon as you possibly can. Not trying to scare you guys, just being brutally honest. This is easily the difference between an A and a B or a B and a C in this class. So if you have any questions about it, all the way throughout the entire quarter, do not feel embarrassed to ask about it. I have presented it simply here, but in practice, even I still make mistakes on occasion and all that kind of stuff. So it's nothing whatsoever to be embarrassed about. If it doesn't make sense, please ask. While I am a jerk, I try to be an approachable jerk. Okay, so all right, so let's put this into use by looking at one of your web work problems. And this will lead me to the last topic, and then I've ranted so long, I don't know that we're going to have time for the in-class assignment. Yeah. Oh, we might be able to, yeah. So let's look at homework set 1. Let me find one of the problems. This will work. So in the figure below, we are given the value for voltage V1, current I1, V2, I2, V3, and I3, and all of that kind of good stuff. We are asked to find the power absorbed by the circuit element A in the figure below. So I'm going to start by asking a simple fundamental question, and I'm going to pick on the people who, unfortunately, I already know their names. So over time, everybody will get picked on. Abram, for part A, is that current I1 flowing into the positive polarity terminal or the negative polarity terminal of that weird seven-sided element thing? It's flowing into the positive polarity terminal. So since I am trying to find absorbed power, would I need to introduce a negative sign or simply multiply whatever I'm told for V1 by whatever I'm told for I1? Just multiply it straight up, don't add a negative sign. Absolutely correct. All right, let's see, who else? Patrick. For element B, is the current flowing into the positive polarity terminal or into the negative polarity terminal? Flowing into the positive polarity terminal. Since we're asked to find absorbed power, do I need to add a negative sign or not? I do not, okay? Hannah, for element C, for element C, is the current flowing into the positive polarity terminal or the negative polarity terminal? Flowing into the negative polarity terminal. Since I'm asked to find supplied power, do I need to add a negative sign or not? I do not. That's all this takes. It's annoying for sure to have to do this all the damn time, but that's literally all the passive sign convention does. Look at which direction or which polarity terminal the current is flowing into, and then figure out based on the quantity that you're trying to solve for, whether or not you need to add a negative sign. If you can do that consistently, you're done. Passive sign convention is great. Congratulations on probably an A in the class. Like, we only marginally get it. All right. So let me stop there because we do have a mini lab and all that kind of good stuff. So that's enough ranting out of me for today. If anybody has any questions, I would be more than happy to answer them. If not, work on the mini lab, work on the in-class assignment, have a great weekend, all that kind of good stuff.